Today we're going to learn about electron configuration. So here we have the periodic table, and we have it color-coded into S, P, D, and F blocks or sublevels. So you do want to actually color in a printed periodic table if you have not already and label these sections. And then I recommend putting it in a sheet protector so that you can mark off your target areas and practice these. So we have some numbers and some key terms. One's the quantum number, and that's the ring the electron is found in. So if we're looking at the S and P levels, they are going to match. So in period 2, that is also ring 2 because those guys are all S and P blocks. But when you get into the D block area, you would actually need to subtract 1 off the period number to give you the quantum number or the ring number that electron it is in. Okay, your sublevels are your SP and D, SP, D, and F blocks, and that just gives you the shape of the orbitals. So the S sublevel on period 2 is going to give you 2 sphere-shaped areas that those electrons can travel in. And each box on the periodic table is going to represent an electron. So hydrogen, 1 electron in its ground state, helium, 2 electrons in its ground state, lithium, 3 electrons in its ground state, and so on and so forth. So when we do electron configuration, it's kind of like a dance that I call the row, block, box dance, because you're going to keep repeating that same process every time, and you're going to start at row 1. So let's do some practice. How about carbon? Okay, so carbon, row, we start at 1. Carbon, row 1. What block is he? Block means that SPDF. So I go look, that is the S block. And then how many boxes are in the S block for row 1? 1, 2. And I use a superscript for that. That represents the number of electrons. So the S block in row 1 has 2 electrons. Row 2. What's the first block we get to? The S block. And how many boxes are in the S block? 1, 2. So I put a 2 for a superscript. I'm not done yet. You got to go in order the whole time till you get to your target area. So I'm still in row 2. I am now in block P. And how many electrons are in block P? I'm only going to count 1, 2 because my target is carbon. So there are 2 electrons in the 2p sublevel for carbon. There can be a maximum of how many electrons? 1, 2, 3, 4, 5, 6, but we're not filling up all of those boxes, so we're not worried about those electrons. Carbon's ground state electron configuration is 1s2, 2s2, 2p2. All right, let's pick somebody else. Calcium. Row, block, box. Start at row 1. Row 1. What's the block? S block. How many boxes are in that S area? 1, 2. So that's the 1s2. Row 2. We're starting with that S block again. How many are in S? 1, 2. Still in 2. We're going in order of the periodic table. Row 2. We're now in the P block. How many electrons? 1, 2, 3, 4, 5, 6. So we went past carbon this time because this time we got to get all the way to calcium. But notice we started out pretty much the same. Row 3, block S. Boxes. How many boxes? 1, 2, 3s2. Row 3, block P. Boxes 1, 2, 3, 4, 5, 6. 3p6. Row 4, block S. make sure you count the electron that we're on. So 1, 2, you count your stopping place. You count your target. So calcium has a ground state electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. How can we make sure that we're doing this correctly? Add up your boxes because your boxes are electrons. 2 plus 2 plus 6 plus 2 plus 6 plus 2 gives me 20 electrons because I've done 20 boxes. Lo and behold, calcium here is number 20. So in its ground neutral state, there's 20 protons and there's 20 balancing electrons. So that makes sense. What else can we do with electron configuration? Well, we have 4 laws here that we have to discuss. Which law is going on in this picture? So if you don't remember your electron configuration or you don't know your German, this one's going to be hard to guess right off the bat. But we are building the order that the electrons go in. Off-ball just means to build. Okay. What's really, really awesome is the periodic table goes in off-ball order. So you do not have to write out this chart every time and use it. You can just use the periodic table to make sure you're not messing up your order. And again, that's off-ball order. So let's do a couple more here. This time we're going to do some orbital diagrams too. And we'll get to that after we draw out the electron configuration first. So who haven't we done yet? Let's do magnesium. Start at row 1, row, block, box. Magnesium, row 1, S block, 1, 2 boxes. Row 2, S block, 2 boxes. Row 2, P block, 6 boxes. Row 3, S block. How many boxes? Make sure you count the one that you're on. 3s2. So magnesium's ground state electron configuration, 1s2, 2s2, 2p6, 3s2. We followed off-ball order automatically because we started with 1 and we started with hydrogen and we went through the boxes. If you use any other order, it is not off-ball and it is all wrong. So make sure you are following that order. Some people like to simplify and not put the row each time. That does not count because remember, this row is actually your quantum number. Okay, and your quantum number is not always the row number. Remember, we have that D block, subtract 1 off of your number to get your true quantum number. So it has to be repeated every single time. It has to go in this order, even if the order does not make sense. Get through the dance. Row, block, box, row, block, box, starting with 1 every time. All right, so now we get to those other rules, Pauli and Hund's, and that is how we're going to represent these electrons. So each arrow that I'm going to put represents an electron. So it represents what? It represents a box on the periodic table. So let's transfer some numbers here. 1s2, so I'm just going to write 1s2, 2s2, 2s2, 2p6, 2p6, 3s2, 3s2. So the 1s2 says there's 2 electrons in the s block in row 1. 2 electrons. So Pauli's rule comes into play first. You can have maximum of 2 electrons per orbital, and they have to be opposite spins. So I have 2 electrons going over here in this orbital box. One is going to be an up spinning electron, one's going to be down spinning. And we're just going to make sure they are opposite spins. You can draw a full arrow, but if you can see, that's why it gets kind of sticky in there and hard to fit. So some time ago, chemists decided, one, it's faster to only have to use it like that, but it also saves them some space. So what about 2s2? What did that mean? That means in quantum number 2, in the s area, the sphere-shaped area, there are 2 electrons. Those 2 electrons have to be one up, one down. 3s2, same thing. So now I have 6 electrons accounted for. How many electrons do I need? Let's go back over here. 2 plus 2 plus 6 plus 2. I'm going to need 12 electrons accounted for. So I have 6 more to go. I have my 2p electrons to split up. These guys follow a different rule. These guys follow Hund's. Okay, they also follow Pauli, but Hund's is the one you need to remember when you're writing it down. You have to fill the ups arrows before the downs. Fill the up arrows in the whole sublevel before the down. So I have 6 electrons. 1, 2, 3. 3 ups first, and then go back 4, 5, 6. So some of you are shaking your head going, no one's going to know that I wrote it that way and I didn't write it this way. It will matter later on. So I still to this day go up, 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 down, 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 even on the ones that I know are completely full. It's just a good habit to get into. Okay, so now I can answer some questions here. If somebody says, how many upspinning electrons does magnesium have? Okay, and in this case, he has 6. So he happens to have the same number, but it does not always work out that way. Okay, so Hund's law, what about if it's in a weird situation? So let's try out some here. If we're in a P3, so it doesn't matter what quantum number, okay, 2p3, 3p3, 4p3. Notice I didn't say 1p3. There is no p sublevel on row 1 because there's only 2 electrons, so they only get an s block in row 1. So p3, up, up, up. How about if I have P4? Up, 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 down. Okay, this is set up this way because we want to have as much equal energy as possible. Now, P3 has perfect equal energy. P4, it's just the best it can do. What about if I had P5? Then I'd have up, 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 down, down. What if I had P6? Up, 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 down, down, down. So these are all set up to help us with our bonding. Pauli, remember, 2 electrons, 1 up, 1 down. Those are a review of the rules that we just drew. Okay, and so you could have these arrows just with a line how it is, or on some programs, they have a little box that you write the electrons in. Either way is fine, as long as you're representing the orbital in some way, and then there's only 2 electrons per orbital, 1 up and 1 down maximum. Okay, so now, if you've been following along, you might recognize that that's going to get really old. If I have to write radium and I got to start with 1s2, 2s2, 2p6, 3s2, 3p6, it's going to get old very, very, very quickly. So we came up with noble gas or abbreviated electron configuration. So whatever guy you have, let's do potassium this time. You look at the previous noble gas. So we're now in quantum 4. We're going to go to quantum 3 all the way to the right and find this noble gas. Remember, group 18, they're called the noble gases. They don't like to react. They already have that full configuration. So the previous noble gas for potassium is argon. Now it's getting confusing because now I have potassium written and argon written. Put brackets around argon. That means that you are going to substitute previous noble gas in brackets and then the valence row electron configuration. What does the valence mean again? That is the outer energy level. So in this case, this would be period or row 4's electron configuration. And I'm still going to go row, block, box. So in this case, I'm only doing the row 4's. Row 4, the block is S, And the box is only the first one. Do count that first guy. So this is the abbreviated configuration of potassium. Some of you are going, I have no idea where that came from. Okay, so let's break that down. Let's do the whole full electron configuration. Start at row 1. S block. How many? 2 in the S block. Row 2. First thing we hit is the S. We always hit the S first. And there's 2 electrons or 2 boxes in 2s. Row 2. P area. 1, 2, 3, 4, 5, 6 for 6 boxes. 2p6. Row 3. S area. 1, 2. Row 3. P area. 1, 2, 3, 4, 5, 6. 3p6. Row 4, S1. Look at that. These are the valence layers. Okay, that is the highest quantum. Okay, only the 4 will count for potassium. Only the 4 will count for calcium, scandium, titanium, vanadium, all the way through to krypton. Their valence 1 is only the quantum number of 4 when you have that coefficient of 4. Okay. We see it in both spots because this abbreviated electron configuration is when we're doing electrochemistry and bonding. We're mainly concerned with the valence ones anyway. So being able to substitute that first part is helpful. Now, how was I able to substitute that first part? Let's go and see what is argon's electron configuration. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. Look at that. They match completely because since we always have to start at 1 and go row, block, box, they are going to be identical up to the point. Everybody starts with 1s2 except hydrogen. He has to stop at 1s1 because there's only 1 electron in hydrogen. So we're starting over at the same part. So these guys are all identical for their inner electrons. So why not just say substitute argon's electron configuration and then write the last row. Okay. Now, when I'm doing this abbreviated form, if I'm going to do my little orbital diagram where we're discussing what the electrons are, I have S. S always has 1 orbital, and in this case, only 1 electron, so 1 upspinning electron. So that's all I would need to show for an abbreviated electron configuration. If I have to do the whole configuration, let's do the whole one down here. 1s2, 2s2, 2p6, 3s2, 3p6. Pauli's rule. Each orbital can only have a maximum of 2 electrons and of opposite spins. 1s2, 2 electrons, up, down. 2s2, up, down. 3s2, up, down. 2p6, Hund's law, fill the ups before the downs. Up, 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 down, down, down. 3p6, up, 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 down, down, down. 4s1 only has 1 going up. So if we count up these arrows, we are going to get 19 arrows for 19 boxes for 19 electrons. Argon is number 18, so it still works here. 18 plus 1 is 19 electrons. Okay, which law is broken here? This is how it should look. That's Hund's law. Fill up the ups before the downs. Okay, now this one on the top here is kind of lopsided, so it's 1 more unstable, but so we have 1 whole empty orbital instead of spreading out the energy. If I use what nature figured out, because nature is smarter than us, but what Hans was also able to prove, I now have 2 bonding spots here. So I'm able to do more things because I have 2 unpaired electrons to bond with, as opposed to no unpaired electrons on the top. So that just makes things a little bit easier. So Mother Nature was smart with that way. How about I have to compare oxygen and sulfur? Oxygen and sulfur. Oxygen right here, sulfur right there. I'm noticing something. They are in the same group. They are in group 16, so they are going to automatically know they're going to share similar properties. So let's go write that out to confirm. Oxygen first, 1s2, 2s2, 2p, 1, 2, 3, 4. Sulfur, starting at the beginning, 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6. We got to keep going. 3s2, 3p, 4. Okay, so they started out the same. Sulfur went further. Sulfur went 8 further. 1, 2, 3, 4, 5, 6, 7, 8, so that he ended up at the same group. If I look at their valence electrons, remember valence are the ones with the highest quantum number. So for oxygen, the highest quantum number is 2. So we have 6 electrons that are valence electrons. For sulfur, the highest quantum number is 3. And again, we have 6 valence electrons. So this periodic table is laid out so well that one of the reasons why they have similar properties is they have the same number of valence electrons. So they're leaving those same electrons available for bonding. So we can have similar bonding occurring. All right, I'm just going to do the sulfur electron configuration just so that you can see it. 1s2, 2s2, 2p6, 3s2, 3p4, 1s2 by poly up and down, 2s2 by poly, 1 up, 1 down, 3s2 by poly, 1 up and down, 2p6 up, 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 down, 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 3p4 up, 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 down. They both are going to have a valence P level that looks like this. Now, oxygen's is going to happen down here in the 2p, but that does not matter. It's still in the outer row. They are going to have up, 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 down for their P levels. So they are going to be comparing those sizes. And so sometimes you're going to see that written just like this. The N just means quantum number. S for the S block, the X is for the electrons in the S block, and the Y is for the electrons in the P block of those valence layers. So they are going to have that same valence electron configuration because they're in the same group. So you're going to have similar bonding, like I said, so you should be able to figure out what group the X imaginary element is in. Sodium has a +1 charge. Magnesium has a +2 charge. Up here, we have a perfect match. So element X is going to have a -1 charge. How about down here? Hey, there's still only 1 atom of magnesium to balance 2 of atom X. So we have 2 positives here. So what are we going to need on the other side? We're going to need 2 negatives, and we have 2 atoms. So there's going to be 1 negative for each one. So that is just another indication that this guy is going to have a -1 charge. That puts him right here. Any one of these guys would bond the same way with sodium. Okay, sodium 1, fluorine 1, NaF. Any one of these guys would give me 2 if bonded with magnesium. Every single time they're going to have those similar bonding because they have that similar valence electron configuration. They have the same number of valence electrons. Now, why is fluorine a -1? Because he only has 7 valence electrons. How do we know that? Let's look at his electron configuration for abbreviated. Helium is the previous noble gas. And then the last row, 2s2, 2p5. 2 plus 5 is 7 valence electrons, so we confirm that. But he wants to be like a noble gas, so somehow he has to figure out how to get to neon. How do I get to neon? I got to add a box. If I add a box, I'm adding an electron. So for him to get to his ion state, he would be substitute helium, 2s2, 2p6 would be his ion electron configuration, because now he's isoelectronic to neon, has the same electrons as neon does. So that is how those ions are going to be helping you out. So let's do a full one here with the orbital diagram. Okay, so let's do calcium again. Since we did that calcium full one earlier, hopefully doing the calcium full one again is going to help you. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Always include that one. So calcium here for his quantum number is for the valence layer, has a quantum number of 4 or ring 4, and he only has 2 electrons in that ring. Group 2, 2 valence electrons. He can't add 6 more boxes. One, he's having to go through a whole heck of a lot to get to krypton, so that is just not going to work. He's going to go the other way around because it's closer to get to be like a noble gas. He has to take away 1, 2 boxes to be like argon and to be like a noble gas. So he's going to lose 2 boxes to be like a noble gas. So calcium has a +2 charge because he lost 2 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, and we don't say 4s0, we just have made him smaller. So calcium, when he's in his ion state, now only has 3 filled rings. So he's actually going to be smaller than his atom state because he has less rings. Okay, and so when I have to do an orbital diagram of the ion, 1s2, 2s2, 2p6, 3s2, 3p6. 2 electrons, 1 up, 1 down, that's poly. 2p6, up, 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 down, down, down. 3p6, up, 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 down, down, down. That number, when I add it up, equals 18 electrons. So looking at just the orbital diagram, calcium's ion state looks identical to what it would look like for argon. That is because calcium in his ion state wants to be like argon. So he's isoelectronic, same electrons to argon. So what's the rule to remember? Draw the full electron configuration and then add electrons if it's an anion, because the anions have more negative charge or more electrons or more boxes. Subtract boxes if it's a cation. So subtract off those boxes off that electron configuration. And have a great day.